Bismillahirrahmanirrahim. So we have previously talked about the theorems. So we started with before that we have explained about the groups and then gave a lot of examples and then talked about elementary properties in terms of these theorems. We have proved these theorems and the cancellation laws, uniqueness of inverses, socks shoe property. Now we will talk about some exercises which we want to discuss. So let's say number one is to show that the set 1, 2, 3 and the multiplication modulo 4 is not a group, but that 1, 2, 3, 4 is under multiplication modulo 5 is a group. Okay, and the solution. So what we need to check is that in the first set, in 1, 2, 3, under multiplication modulo 4, the multiplication modulo 4, 2 does not have inverse. Because there's nothing you can multiply and get. Because when you multiply 2 cross 2 with itself mod 4, you would get 4 mod 4, which is 0 and does not lies in 1, 2, 3. So that is enough. 9. Okay. Now under like under multiplication modulo 5, the set 1, 2, 3, 4 is closed. And to check that, you can multiply 1 and 4 mod 4, you would get 4. And similarly, you can multiply 2 mod 4 to mod 5. Sorry, there should be 5 here. You would get 8 mod 5, that is 3. Anything else like 3 multiply 4 mod 5 is 12 mod 5, that is 2. More 3 multiplied 2. 2 multiplied 3 is 1. So maybe you should write 2 multiplied 3 mod 5 is 6 mod 5, which is 1. Now, this shows 1 is the identity, 1 is the identity, because 1 multiply everything else is going to be similar. Under mod 4, no need to check that. And 1 and 4 are their own inverses, because for the 1 it is fine, but like for 4, you multiply 4 under mod 5, it is going to be 16 mod 5, and it's going to be 1. And 2 and 3 are inverse of each other, are inverses of each other by this. So, and you can also say that multiplication modulo multiplication is associative. That is 2 multiply 3 multiply 4 is actually 2 multiply 3 multiply 4, because 2 multiply 3, this is going to be 1, multiply 4, this is 2, multiply, this is going to be 3 multiply 4 is 2, this is 4, this is 4. So, like that. This is multiplication. Modulo multiplication is also associative, and that's how you check this one. Okay. Then we can talk about that uh, let's say G be a group. Let's say let A and B be elements of an abelian group. It means it follows the commutative property, and let n be an integer, be any integer. We need to show that a b power n is a power n b power n. Now, is this true? Is this true for non-abelian groups? Okay, perfect. So we have two elements of the abelian group. their power is a power n, b power n. And now we also need to make sure that it is true for the, is it make, we also need to find it that is it true for the non-abelian groups. So solution, let's take that for n is greater than or equal to 0, we use induction. And if you want to know what is induction, try to go through the my pure mathematics course and you'll find induction chapter there. The case that n is 0 is trivial, then note that ab power n plus 1 is going to be ab power n into ab, and we can write that a power n, b power n, a b is going to be, if it is, now we can write this a power n, a, b power n, b, and then I can write that a power n plus 1, b power n plus 1. Okay, now this is true when these from here to here, a b is b, a b power n, a is a b, a b power n. So that's commutatively. Abelianness is used there. Now for n is less than 0, note that e is actually equal to ab power 0, and then I can write ab power n into ab power minus n, and then I can write into ab power n into a power minus n, b power minus n, so that so that a power n, b power n is nothing but a b power n. Now the final answer for the non-abelian is in a non-abelian group, a b power n is not need not equal, need not to be equal to a power n, b power n. Okay, perfect. Then we can try few more. And let's say that for any elements a and b from a group and any integer n, prove that a power minus 1 b a power n is a power minus 1 b power n a. Now, again, we use the similar kind of technique. The case when n is 0, it's trivial, and for n is greater than 0, note that a inverse b a power n is nothing but a inverse b a inverse b a times a inverse b a uh, n times. Okay, and so cancelling the consecutive a and a inverse terms, sealing the consecutive a and a inverse, because you see over here these two appears, so they would cancel out each other. Terms give a inverse b power n a. Okay, and for n is less than 0, note that e is a inverse b a power n a inverse b a power minus n, and a inverse b a power n is a inverse b power minus n a. So we get and solve for this. So, and solve for a inverse b a power. That's there you get to go. So this is the answer. Now, you actually now the interesting one is exercise 4 says that let G be a finite group. Let G be a finite group we need to show that the number of elements x of g such that x cube is e is odd. Also, show that the number of elements x of g such that x square is not e is even. Okay, now let's try to show that. So solution, since e is one solution, we are trying to find out the solution. So since e is one solution, e is one solution suffice to show that non-identity solutions come in distinct pairs. To this end, note that if x cube is e and x is not e, then x minus 1 power 3 x inverse power 3 is e, and x inverse are not same. So if we can find one non-identity solution, we can find a second one. So if we can find one non-identity solution, we can find a second one, right? Now, suppose that A and A inverse are A and A inverse are non-identity elements that satisfy x cube is e and p is a non-identity element such that B is not A and B is not A inverse and B cube is E, then is before B minus 1 B inverse cube is B and B is not equal to B inverse. Moreover, B inverse is not A and B inverse is not A inverse. Thus, finding a third non-identity solution gives the fourth one. Thus, finding a third non-identity solution gives a fourth one. Right? Counting in this fashion, we can see that we always have an even number of non-identity solutions to the equation. We're continuing in this fashion. We see that we always have an even number of non-identity solutions to the equation. X cube is E. And so along with the identity solution and non-identity solution, you combine them, the you'll get the odd solutions for the first one. And to prove the second statement, the second statement, note that if x square is not E, then x minus 1 is also not x, and x inverse square is not E. So arguing is in the preceding case, we see that. So arguing in the preceding case, we see that we always have an even number of non-identity solutions. To the equation. X cube is C. Sorry. Uh, yeah. Okay. Then and there we can end the exercise part, or maybe I can present something else. One last one. There is this 5, which can be said that let A, B, and C be solve the equation. Which one? That A x B is C for x, and solve A inverse x A is C for x. Solution. Now A x B is equals to C implies that x inverse, sorry, x is A inverse A x B B inverse, which is nothing but A inverse C B inverse, right? And A inverse x A is equals to C implies that x is nothing but A inverse x A into A inverse, and this is nothing but A C A inverse, and that's it. Okay, so there we would end our this part of the lecture. Thanks so much.